Hello! On this last video for this module, we will be looking at the water and reviewing properties that make it ideal for sustaining life. We will also say a few words about pH scale and acids and bases. Finally, we will talk a little about organic chemistry. So why don't we get started right away? As you might remember, earlier we concluded that water is considered as the foundation of all life. Therefore, we look for signs of water when we are looking for evidence of life, for example, on other planets. On this first part of this video, I want us to review these properties that make water especially great for life. And the first one that we will have a look of is the fact that we know that water is a great solvent. As you probably remember from our earlier discussion in the previous video, we noticed that water is a polar molecule. This meant that the electrons that the oxygen atom and two hydrogens share, so that all of these have a full valence shell, these electrons are unevenly shared. Because these electrons spend longer with the oxygen atom and shorter time with the hydrogen atoms, the oxygen end of the molecule becomes slightly negative, while hydrogens become slightly positive in terms of their charge. This polarity is important because polar substances are especially good as solvents. And as water dissolves so many different substances relatively easily, it is often referred as a universal solvent. In fact, it dissolves more substances than any other liquid. As a side note, here you can see also a picture of an experiment that I did some time ago, and we found that the colors of these trees remained as relatively distinct regions with what appeared as a sharp, well-defined lines. We had a few theories as for why that was the case and looked into it a bit more, but that's a whole different story. Another characteristic of water that I wanted to discuss about is cohesion. Have you ever done that? Is that you would overfill a glass with water, yet the water does not overflow, but rather forms a slight elevation, which, without a doubt, is above the edges of the water. It's magic, you might say. Well, I hope not. I often say that the world seems to be a very magical place for those who do not understand science, but I hope that we can do better than that. What we are seeing is because of cohesion. This refers to the fact that water molecules stick to each other, and this, of course, is due to the hydrogen bonding, which we just talked about in our earlier video. We will next have a look of adhesion. Thanks to adhesion, water also sticks to polar surfaces. Here we see a very good example of adhesion, as the water droplets stick tightly to the leaves, even when they are in such a steep angle that they should fall off the leaves. Another time when we see an example of this is the concept of capillary action in a glass tube that has a small enough diameter. What we notice is that the adhesive forces excreted by the internal surface of the glass end up exceeding the cohesive forces between the water molecules. As a result, the water seems to climb up this narrow tube. Let's have a look at the surface tension. A good and quite commonly used example of this is the fact that many small bugs are able to walk on the surface of water. This is because the water molecules cling together very tight, especially at the surface of water. Have you ever wondered why the climate seems to be so ideal at the coastal California with nice and fairly even temperatures not only throughout the year, but also having very little changes between night and day? And then here in Arizona, it can get roasting during the day, but once the night arrives, it can get freezingly cold. Why is this? Why do so many people prefer the climate of California? Well, this has all to do with the capacity of water to work as a heat reservoir. Water can both absorb heat and then release it. And we see just that in the coastal California. During the day, this big body of water absorbs a lot of the heat, and then during the night, it slowly releases it. This way, the changes in temperature are slower and lesser. And since we do not have a lot of water here in Arizona desert, this does not really happen here, and the changes are more extreme. And we use this ability of water to absorb and release heat in many applications. Think of heating systems where the hot water travels through radiators, or hot water bottle for that matter. Really, the ability of water to store the heat is due to the fact that these changes take place slowly. Well, now we have gotten to the fact that water takes different forms. And we saw this illustration already earlier on our videos. So of course, we know that water can take solid, liquid, and gas form. This all is very useful as well. And then the final one that I want to mention here is the fact that water acts as a great transport media. For example, our circulatory system uses blood as a transport media, and this is because most of the blood is water. And plants use water to transport nutrients from the soil. Again, as a side note, here is a picture of an experiment that I do often do with my students, where we use different food colorings in water and then let the plant to take up the water, and we can see the difference in color of each plant. So, now that we have covered all of these important properties of water, I hope that we can see that there really is no substance as ideal for supporting life. We have already earlier mentioned that water is polar. This polarity of water causes another important characteristic that we really ought to at least recognize here. So some substances are known as being hydrophilic, and this means that they are attracted to water. They love water and want to be in contact with it. While others are hydrophobic, this again refers to these avoiding water. This is easy to remember by thinking, what do you do when you have a phobia of something? Well, you try to get away from it. You might wonder why this is important, and we will get to that a little later in our course, but when we look at the structure of a cell membrane. But for now, I would like you to know that these two terms exist. So I guess that many of us have seen pictures of icebergs. And as we are talking about water and earlier mentioned the different phases of water, I want us to think about this for a moment. And I dare to claim that most of us think that it is obvious that ice floats. After all, we have seen pictures of these icebergs which float on the sea. So my question is whether we can use what we have learned so far and use it to explain why ice floats like this. Let's give it a go. So let's start with what we know. I think it's always a good place to start. To explain this question, we know that we are looking at water in a solid phase as ice, and we will be looking at water also in a liquid phase. So the explanation must lie somewhere in between these two. Let's consider that further. When we look at the arrangement of water molecules, we start to see our first clue to this question. Clearly, in liquid phase, water molecules seems to have been packed not only randomly, but also closer together. When we compare that to the solid phase, which would be ice, of course, we notice that the arrangement of water molecules takes a hexagonal shape. We also notice that in this case, there is a greater distance between the water molecules. And this makes sense. We all know that water expands when it freezes. And the key to figuring this out is in that sentence. Let's think of it a little more. Water expands when it freezes. But what does that sentence really tell us? It tells us that the same amount of water will now take a larger volume when it comes from liquid to solid ice. And we can of course explain this with what we just noticed about the arrangement of the water molecules. We can see many examples of this, especially when people have accidentally overlooked this fact. I think that most of us have seen, or at least been told, what happens when you put a bottle of a drink in a freezer and it has not got enough space in a bottle to expand. Yes, we get quite a mess as the frozen water expands and breaks the bottle. Or you might have heard that we should drain the hoses and pipes before it gets to a freeze night, right? Again, this is because the force of the expanding water is so great that it can easily break the pipes, and the consequences can be quite a mess. So I think that we can agree that this topic has relevance to us, not just in terms of icebergs. Let's jump back here. And if we apply what we just concluded a while ago about these pictures, we can conclude that liquid water is more dense and ice is lighter. Therefore, understandably, ice must float on water. So there's our answer. In the past, I have used this as an exam question, but that is not a guarantee that I will do it this time. Nor is it to say that I would not. Make what you wish out of that comment. So that's what I wanted to speak about water. Now, let's move on to look at the concept of pH and something being acid or basic. Next, I want us to talk about pH scale, just a little bit. And before we figure out the definition behind it, let's review the basics. pH scale runs from 0 to 14, with the middle point, pH 7, being neutral. Anything with a pH below 7 is known as acidic. Some of the examples of materials that fall here are hydrochloric acid, and this is of course found in as a stomach acid, lemon juice, various drinks like Coca-Cola and beer, vinegar, also tomatoes, coffee, and urine. What is common to all these acidic substances is that there is a lot of hydrogen ions in these substances. How about the other end of the scale? Let's have a look at that. Well, substances with a pH above 7 are known as basic. Some examples that I can think of would be sodium hydroxide, oven cleaner, it's a strong one for sure, bicarbonate of soda, ammonia, even baking soda, and how about seawater? All of these substances share something. They all had little hydrogen ions. So this comparison of acidic and basic substances gives us an indication of what pH scale is really all about. It is simply a mathematical way of showing the number of hydrogen ions in the substance. So one way to describe it would be to say that pH shows the proportion of hydrogen ions in a substance. And just as a reminder, if you overlooked that, hydrogen ions are symbolized here with a capital H and superscript plus. So that's our pH. And one of our later labs is going to be looking at pH. But there is something related to that I want us to note. The concept of buffers. Buffers are chemicals or chemical combinations that function to keep pH within normal limits. And like I said, we will use one of our labs to identify what would be good buffers and what would not be very good buffers. The clinical relevance of this is a condition called acidosis. Acidosis is basically when your body fluids contain too much acid, so acid builds up in blood. Some causes that are relevant include excessive loss of bicarbonates from the blood, which is known as metabolic acidosis, or buildup of carbon dioxide in blood, which would result from poor lung function or depressed breathing. And this would be known as respiratory acidosis. I have listed some signs and symptoms here, and as you can see, they are varied and can vary from mild to some really serious things. So how do we diagnose this? Well, mainly blood work and urine analysis. And treatment would depend on the cause. You might wonder if you need to know this stuff about acidosis, and the answer is that I would not expect you to know it at this level. It is only provided to give you a clinical reference for what we have been talking about. The very last topic that I want to cover with you is about organic chemistry. So let's have a look at that. Let's start by thinking what is organic and what is inorganic. Well, stuff that has a living origin like plants, animals, dead material, waste products that can get turned into nutrients and so on. All of those are organic. While inorganic substances are typically non-living sources like rocks, minerals, glass, ceramics, metals, and so on. As a side note, I have been recently very entertained by seeing in the shops that salt is apparently non-GMO. As far as I know, salt is not an organism, so it has no DNA. So there is nothing to genetically modify in the first place. This just shows that everyone should really take science classes, I guess. But the classification to living and non-living origin does not really help us. Organic chemistry is all about molecules that contain carbon and potentially hydrogen. The fact that a substance has carbon is something that we want to note here and connect to what we have learned so far. Carbon atom has 4 electrons on its valence shell. This makes it very reactive and likely to easily form covalent bonds. And because carbon is so vital for organic chemistry and the molecules and macromolecules formed in it, we sometimes talk about it as the backbone of organic chemistry. There is one more important term that I want to talk about. And to consider it, let's think of a substance that has the exact same number of carbon atoms, in this case 6 of them. But look how this can take many different forms, and these different forms mean that it would behave differently, so have different functions. And these would be known as something called isomers of this substance. So there are the same chemicals, but the molecules made can take varying different forms. As the very last thing of this video and our chapter material, I want to discuss briefly about something called functional groups. These are certain groups of molecules that when added to the carbon backbone always tend to affect similarly, and usually this effect is in chemical reactions. So you can think of these as helping us to predict the chemical reaction that will take place. And I have provided a nice table of some of the most important ones here, but you will also find it in your learning module to download. And that concludes our review of all things chemical that play a major role in our study of life. I know that it has been a jump away from what you were expecting when you signed up to a biology class, but now that we have reviewed these, we have a strong foundation to build on these as we move to increasingly larger and larger scale of study of life. Thank you for having joined me on these videos. We will see you in the next module.